Good afternoon, everybody, or good morning, wherever you are. Welcome to another edition of Taco Tuesday. My name is Brett Zerba, and my co-worker, Rich Medairos, will be on the line shortly as well. Before we get too far into the presentation, we see some people still logging in, so let's go through some housekeeping arrangements here. Number one, let's make sure that you folks can hear me. So there's up in the dashboard, and some of you have been through this before. If a couple of you can raise your hand, please raise your hand. Let's see. I see Jason Barlow. Good, my good friend Jason raising his hand, and others. So I'm sure that means you, most of you, if not all of you, can hear us. So that's good. And Rich will ask if you can see a screen, but I'm sure you can see a screen as well. And then some people typed in the question area. So today's presentation is on the fundamentals of hydronic piping systems, pressure loss, drop, manual calculations. And Rich will get into the meat of that very shortly. And just a couple other housekeeping things, questions, okay? I'm gonna be monitoring the questions, and Rich and I will bring those up as we go, or I'll bring them up to him. So please get familiar with typing those in. When you can, when you have a question, and we'll bring them up. And if we don't get to them, some of you know that we will be, we answer them after. We'll send you an email with the answer. So we try to get to them all, but every once in a while we can't get to them all. So just keep that in mind. And then two other things. Tomorrow, roughly 24 hours from now, or it could be 1 o'clock Eastern time, or 12 o'clock Eastern time, you should get an email if you've signed in and logged in that will include a link to your certificate, your one PDH hour certificate that you may be able to use for your state requirements, and also a link to the video. We are taping this, so there is a link for that. And by the way, you can go back and review any of the Taco Tuesday webinars through the Taco website, tacocomfort.com. And if you get to the Taco webinar page, Taco Tuesday page, if you scroll down to the bottom, it'll have an area where you can get to any other of the webinars that we've had. So we've had quite a few, and this week is a commercial one. So without further ado, I think I've covered everything. And again, thank you very much for attending. We appreciate everybody popping in here. And other than that, Rich, take it away.
Well, thanks, Brett, and welcome everyone to Taco Tuesday. And today's topic is all about the pressure drop calculations, and we specifically are covering the manual calculation process. And a quick housekeeping thing. Like Brett said a moment ago, if we could just make sure everyone can hear us okay, if you could just type into your little question, or I guess you can wave your hand in this case. Is that right, Brett? You can wave hands.
Yep, I see. Okay. People are typing in and people are waving hands, so I think everybody's good.
Okay, great. You can hear us and see us okay. That's excellent. All right, so getting started here. Let me just get my screen cleaned up. There we go. All right, so we are talking about the manual pressure drop calculations. So let's just highlight some of the items we'll be covering. Oh, I forgot to introduce myself. I'm sorry. This is Rich Medairos. Ta-da! And I'm with Taco, I'm with Taco Comfort Solutions, one of the Taco family of companies. All right, great. So we'll get right into it here. If I can get the computer to work. Ta-da! The computer is now working. So we're going to talk a little bit about water velocity pressure, pipe pressure losses, fitting pressure losses, valve pressure loss, what is CV all about, and then questions at the end. So let's start right off with velocity of water. So we have an example here of a 6-inch diameter Schedule 40 steel pipe. And we want to find the velocity if the flow is 500 gallons per minute. Well, before I get into the meat of this we're going to touch base on a couple of formulas, and the main reason for this is to show everyone that this information is not, we don't make up this stuff. It's all based on very basic fundamental science, and the equation should be fairly straightforward and easy to understand. And we'll get into the meat of the pressure drop calculations in a minute. But one of the very first pieces of information we need to find out is the velocity of the water that flows through whatever pipe you have in your system. So in this case, we're going to, as I said, start off with a 6-inch Schedule 40 steel pipe at a flow of 500 gallons per minute, and we want to find the velocity in feet per second. So the equation is, initially rather, we need to calculate the pipe internal area in square feet. So if you notice on the right-hand side, let me get my little pen here. If you notice on the right-hand side, it says the inside diameter of this pipe is 6.065 inches. And so even though the pipe is 6-inch Schedule 40, the outside diameter is 6.625 inches, but the inside diameter is 6.065. And this is called Schedule 40 pipe or standard pipe. So whenever we think about velocity, we always have to think of the inside diameter, because when it comes to standard, or when it comes to piping system, the especially steel piping systems, they're all the same outside diameter. So in other words, a 6-inch pipe at Schedule 40 has the same outside diameter as a 6-inch pipe at Schedule 60 or Schedule 80. But the inside diameter changes because the wall thickness changes. So in our case, the Schedule 40 pipe, the wall thickness is 0.280 inches. Okay, having said that, let's go to the next little piece here. The internal pipe diameter in square feet is equal to pi d squared divided by 4 divided by 144 to convert from square inches into square feet. And if we just simply plug in the numbers over here, the only number we really have to plug in is pi and also the diameter, and calculate that. If you use your calculator and just plug in the values here, you'll come up with an internal area of 0.2006 square feet. Now, the next thing we want to figure out is, what is the actual velocity? Well, the velocity is equal to the flow divided by the square footage. And we have this constant here, 449.4, and I'll show you in a second where that comes from. So if we again plug in the numbers, we come up with a velocity of 5.55 feet per second. So when I say plug in the numbers, we're plugging in 500 gallons per minute and divided by this value over here. And we're saying that the 449.4 is the conversion from gallons per minute into cubic feet per second. Because if we have cubic feet per second divided by square feet, then we'll get feet per second. And that's where that 449.4 is 7.49 gallons per cubic feet times 60 seconds per minute. And it comes out to a constant of 449.4. And the units, believe it or not, are gallon seconds per cubic meter. I'm sorry, per cubic minute. All right. And if we look that value up on a table, let me erase some stuff over here on the right. There we go. There are lots of these published tables out. This particular one I downloaded from the internet, and it shows the relationship between the pipe size over here. Let's highlight a few items here. In our case, we had 6-inch pipe. I'll highlight that. And we're running at a flow of 500 gallons per minute. And so if you look at the velocity, that's this column over here. Again, this is Schedule steel pipe, Schedule 40 steel pipe. And the velocity, you know what? I'm going to change my pointer here. Let's go to a pen, make it a little easier. Yeah, we've got 6-inch pipe. We're running at a flow of 500 gallons per minute. And the velocity for Schedule 40 pipe, that's right here, is, just as we calculated, 5.55 feet per second. And that's based on those formulas I showed you a minute ago. So again, these tables, you can download them from the internet, whether you're using international SI units, System International, or IP, inch pounds. You just look up, you can type it into a web browser like Google, and you can just say, pipe pressure drop tables, and you'll find them in a variety of different units and configurations. It only took me a couple of seconds to find this one. Okay, so that is the velocity. Any questions about how I came up with the velocity and how I also checked it on a chart, which I was easily downloaded from the internet? Any questions out there,
right.
Brett?
We do have a question, so let's see if I can. Liquid water is effectively incompressible. Do we have to adjust for temperature or pressure? We don't have to adjust for temperature or pressure. Did that make sense? I can read it exactly, yeah. What. Okay.
Yeah, so when we're calculating velocity, we're calculating it based on the volumetric flow. So in other words, in this case, we're converting gallons per minute into cubic feet per second. And that is, since it's a volumetric relationship, you don't have to compensate for temperature. Now, if you were calculating the mass rate of flow in pounds per hour, then you would have to compensate for temperature. So in this case, the velocity is a function of the volumetric flow and not based on the mass rate of flow. Hopefully that answered that question.
Yep.
Okay.
We have another question. Let me see. I got to open it. Is there a reference to maximum feet per second for certain pipe sizes?
Yeah, actually, I have some guidelines as we go through this little presentation. I'll tell you what the general guidelines are. Most people design for hydronic systems. They design for a velocity range somewhere between 6 to 10 feet per second. And most people will design for pipe velocities of less than 8 feet per second. So that's probably the most common for hydronic heating and cooling systems. When it comes to plumbing systems, they generally use a much lower velocity, but for standard HVAC heating and cooling systems, less than 8 feet per second is the most common value. Now, if I'm designing, by the way, a variable flow system, for example, either hot water or chilled water for building heating or cooling, I might actually select my pipe size based on 10 feet per second, knowing that in a variable flow system, the velocity very rarely runs at 10 feet per second because the number of hours in a year that you wind up with peak load is very, very small. It's probably less than 1%. And so you never really reach the full flow in gallons per minute for the overwhelming majority of hours. So in variable flow systems, I tend to use a higher velocity.
Any chance, Rich, you can just go back? A couple of people asked to look at that formula in a little greater for a few more seconds. Can you just go back one slide? Yeah, there you go. Yep. So maybe keep that on for a second or two. Yep. Oop.
Oh, no, I went back. I went the wrong way. There it is. Sorry. So again, the velocity is equal to the volumetric flow divided by the cross-sectional area. And yep. Since the volumetric flow wants to be in cubic feet per second, and we're using the units of gallons per minute, we have to use the conversion from gallons per minute into cubic feet per second. And then if we take the volumetric flow and divide it by the cross-sectional area, that's how we find out what the velocity is. Does that help?
Yep, excellent. And then, okay. And then we're assuming that the pipe is full, correct?
Correct, yes. Yep, no air in the pipe.
Yep, I got a thanks. So yes, thanks for showing this screen. So. Okay.
So again, you can either do the calculation manually like I showed you here, or you can simply look it up in a table that there's dozens and dozens of them out there available on the internet. So it's no mystery as to how you can get this information. All right, so the next piece of information, which is also useful, is to figure out what the velocity pressure is. And so again, given a 6-inch scheduled 40 steel pipe at a flow of 500 gallons per minute, the velocity pressure or head in feet is equal to the following equation. It says that the velocity pressure is equal to the velocity squared divided by 2 times the gravitational constant. And in this case, we just said that the velocity was 5.55 feet per second. If we square that and divide it by 2 times the gravitational constant is 32.2, so that's 5.55 squared divided by 64.4. And you'll find out that the velocity pressure is 0.479 feet. And like I said a moment ago, the G in this case stands for the gravitational constant of 32.2 feet per second squared. Let's go now look at that same table that we had a minute ago. And we're looking at the same pipe, 6-inch pipe here. And again, it's schedule 40 steel pipe. Just kind of repeating a couple of things. 500 gallons per minute. And there is the velocity pressure, 0.479 feet, velocity head or velocity pressure, right there. So you can, again, you can calculate those values or you can look them up in the table. And these tables, this table that I'm showing you, is based on that calculation that I showed you in the previous screen. So this calculation, doesn't want to go back. Let's see if I can erase this for a minute. Yep. So this calculation is, this table rather, is based on this previous calculation. Any questions about velocity head? Okay.
Nothing I see, sir.
All right. So let's continue right along here and let's talk about the pressure drop through fittings. So when we actually do the pressure drop calculation, the manual calculation in a minute, we're going to use what is known as the equivalent length method. And that's this method over here. It says that for every fitting in our system, it has an equivalent length of straight pipe. So for example, the first standard elbow, this is a 90-degree standard elbow. And in our case, we had 6-inch pipe. So let's go over here, 6-inch pipe. And if you'll notice, the pressure drop is, I'm sorry, the equivalent length of this would be equal to that 190-degree elbow would be equivalent to 16 feet of straight pipe. We'll get into that in a few minutes. And if you'll notice, each one of these different pipe fittings has a different equivalent straight run of pipe. So one of the questions I get all the time is that, oh, I've got multiple 90-degree standard elbows in my system and I seem to have an excessive pressure drop. What can I do about that? Well, assuming again that you're working from design and you're not trying to retrofit something that's already been built, you might consider going to a long radius elbow instead of a standard elbow. So a long radius elbow has a shorter equivalent length of straight pipe. So the standard elbow was 16 feet, the long radius elbow was 11 feet. So you can see that that can be significant in terms of the equivalent length. Now, the other thing I wanted to point out, if you'll notice, I have a gate valve over here in this chart. The gate valve has an equivalent length of straight pipe of 3.5 feet. But if you'll notice, the guy right next to it, the globe valve, has the equivalent length of 160 feet. So if you have a globe valve in your system, the pressure drop associated with the globe valve is quite high. So out of all the different fittings that are shown here, the globe valve has the greatest amount of equivalent length of straight pipe. So in other words, the pressure drop across the globe valve, excuse me, would be the same pressure drop that you would find in 160 feet of straight pipe. Again, in our case, 6 inches. And again, you can download these charts from the internet. They're readily available. And you can, in this case, this is in equivalent length of straight pipe. and that's in feet. Okay, erase that.
Rich, just to kind of bring up a basic question here. The reason why you're doing this, or we're teaching people how to do this, is to get the numbers associated with the values to size the pump, right? Is that
Correct.
one of the reasons why? Correct?
Yes. In a minute, you'll see a diagram where all this stuff starts to get pulled together. Okay, so let's look at one other value that's common, is called a valve CV. And by definition, the valve CV is equal to the flow in gallons per minute at a 1 psi pressure drop at 100% open. So if a valve has a CV, in this case, let me just highlight that so you'll know what's going on here. If a valve has a CV of 25, that means that at 25 gallons per minute flowing through that valve, it has a 1 pound per square inch pressure drop. So whenever you see a value for a valve, and generally speaking, most control valves have published CVs. If you had a valve, for example, and I'm going to write on the screen here, of 35 feet, I'm sorry, have a CV, if the CV, it's this little gross, I apologize, was equal to 35, that means that that valve will allow 35 gallons per minute, 35 gallons GPM. These are kind of gross letters, Brett. At 1 PSI. PSI. So what's cool about the valve CV is that whenever you see the CV for a valve, you know exactly what the pressure drop is at that given flow. So you know that if the valve, whatever it happens to be, in our case, I just arbitrarily picked 35. That means at 35 gallons per minute, the pressure drop is 1 PSI. The CV was 40. Then the pressure drop would still be 1 PSI, but now it would be at 40 gallons per minute. So that's where you can get the pressure drop. And generally, it's not something you can calculate. It's something that has to be published by the manufacturer of the valve. So any questions about where CV comes from?
Nothing about CV, but I guess one of the general questions is, there's different charts out there. You downloaded one, and other people may publish different charts. You think some of the values could be different based on manufacturers of equipment or material or whatever?
Well, the charts that I showed you, let's go back here. Generally speaking, this chart is a fairly common chart that's used in the industry for equivalent lengths of fittings. And the other chart that I showed you, with the exception of the friction loss, let me just highlight that. Depending on, in this third column, which we haven't touched on yet, which we will in a minute, the friction loss can be higher or lower for a given value. So in our case, we had 500 gallons per minute, and the friction loss would be 4.16 feet per 100 feet. All right. And however, the other two values would not change. In this case, the velocity in feet per second, well, that was a 5-inch pipe, and the velocity head, in this case, 0.999 feet. So the only thing that would change from one chart source to another would be the friction loss, and that would be depending on how conservative or which equations the manufacturer used or the person that created the chart, because there are several methods for determining the friction loss in feet per 100 feet. Hopefully that answers the question.
Yep. And then if for a valve with a CV of 35, what is the pressure drop at 17 at 0.5 GPM?
That's a good question. Let's see if I can go to the screen where we were a moment ago. So there's the CV. And so what was the value, Brett, that they had?
Half of it, 17.5.
Okay, so what you have to do is that you have to use this equation that says that the pressure, we'll call it the head, at 0.2 is equal to the head, the initial pressure, times the ratio of the flow squared. So if your initial flow, if the CV had a valve, let's say of 25, it was 35, right? So if it had an initial, the CV of the valve was equal to 35, then it would have a 1 pound pressure drop at 35 gallons per minute, PSI. So if we dropped the flow through that valve to 17 feet, then it would be 17 divided by 35 squared. And put my calculator down. Hold on one second. I gotta get my handy dandy calculator out here. So 17 divided by 35 is approximately 0.5. It's a little less than that, squared, multiplied by the initial pressure of 1 pound, and the new pressure is 0.23, we'll call it 0.24 in this case. So the final pressure is going to be equal to 0.24 PSI. Ta-da! Does that answer the question?
Yes, it does. That answered quite a few, so that was good.
Cool stuff. Okay, erase all this. So one last thing I want to show you on this slide, and that is that I'm using the inch pounds in the metric system. It would be cubic feet per hour at 1 bar. That would be the C, it's called a kV, and the conversion is this little table here. So if you're converting from CV, which is in inch pounds units, to kV, that's the kV would be equal to 0.86 times the CV. And if you had the opposite, if you wanted to find the CV and you were given the kV, excuse me one second. If you were given the kV, you'd multiply by 1.17 to get the CV. So that's just the conversion between those two. Okay, here's a little chart from one of our little table rather from our zone sentry valve. And if you'll notice, for the different valve sizes, we give the value for the CV, the kV, and the feet of equivalent pipe length. So this first value, 4.9, let me get the little highlighter over here so you can see what I'm talking about. So if I had a 1/2 inch pipe, its CV would be 4.9, its KV would be 4.3, and the equivalent length of straight pipe would be 9.5 feet. So, and again, the valve CV comes from the manufacturer. In this case, it's us from TACO, but every manufacturer that makes a control valve will publish the CV values. If they should publish it, let me rephrase that. They should publish it. It's not something you should calculate or can calculate. They should publish it. And they're doing that by taking measurements in their laboratory. Okay. All right. So now that we've gone through some of that basic stuff, we get that fun stuff out of the way.
Rich, can you just go back one page just for a second?
Sure.
Someone just wants to take a picture of that one. Yeah. This one here has a lot of information on it, so I think somebody just wanted to get a picture of it. So, okay, thank you.
Yeah, so if you wanted to find the KV for a valve and you were given the CV, you'd multiply by 0.86. So if you'll notice over here, 4.9, 4.9 times 0.86 is approximately 4.3, rounded off. Okay, continuing on. So here we have, for the first time, now we're starting to get into the meat of things. Here we have a simple, very, very simple piping diagram. And in this particular case, the piping diagram has a boiler. It has a circulating pump. It's got pipe. with a bunch of fittings, elbows in there. It also has a control valve. It has an air and dirt separator and an expansion tank. So we want to figure out what the pressure drop would be for this entire piping system, including the pipe, the fittings, and the equipment. So the very first thing we do is once we create this piping diagram, I created this diagram using our HS2 software, but you could just draw this out, sketch it out by longhand or whatever method you're using to represent the actual piping system. And in this case, I know what the load is. It's 600,000 BTUs per hour, and I've calculated the flow in gallons per minute. I'm not going over those details in this presentation because this is all about pressure drop and not about capacity and load. So now I have an established flow of 61.5 gallons per minute, and I've decided to use 2.5-inch pipe, and I'll show you in a few minutes why I decided to use 2.5-inch. But the very first thing I want to do is number my piping system from point to point. And my very first point would be, and this is a bit arbitrary, but I'm going to pick it at the discharge side of the boiler and call that point 1. So I'm going to fill in all of the points by numbering them. So here goes, with a little luck. Oh, that's the other thing I want to say. So in terms of sizing this pipe at 2.5 inches, I wanted to have a maximum velocity of 8 feet per second. So in other words, I wanted a velocity less than 8 feet per second. And I also wanted to meet the criteria of maximum pressure drop of 4 feet per 100 feet. So then I went into that chart similar to the one I showed you a moment ago, and I said, okay, I've got just over 60 gallons per minute. So I go over here to a chart and get my highlighter. And here I have 60 gallons per minute, and I want to have a velocity of less than 8 feet per second. Okay, so the velocity for the 2-inch pipe up here is 5.74, but the pressure drop in feet per 100 feet is around 6.59. And I wanted to have a maximum pressure drop of 4 feet per 100 feet. So 2-inch pipe is not going to work in my case. So I go over here to the 2.5-inch pipe. And again, I go to roughly 60 gallons per minute. And obviously I'm going to make the criteria of less than 8 feet per second, which in this case is 4.02. But my pressure loss is 2.72 feet per 100 feet. So that's why I decided to use 2.5-inch pipe. And there's my 2.5-inch pipe value up there. So now that I know what the pipe size is, I'm gonna erase all this stuff. Now I can go on to numbering my piping system. So here's the first point here, leaving the boiler, I call that point number 1. Entering, let's see if I can use my pen here so it makes it a little more obvious. So I'm leaving the boiler, I'm simply numbering the points on the piping system. And I started here at number 1. Let me pick a different color. I want a different color today, Brett. Can I get a different color with this thing?
I think so, but you can, maybe not.
I can't. Oh, wait a minute, I can. Look at that, son of a gun. All right, so let's try erasing this. Erase all. And let's see what my color came out to be here. Yeah, I'm gonna use red. I love it when a plan comes together. Okay, so this is point number 1 right there. And then if you follow the pipe along, it goes through a couple of elbows and then it connects to the pump. I'm now at point 2. And then on the discharge side of the pump, that's point number 3. I'm just simply numbering the points in the piping system. I'm not numbering the elbows, but the major connections. So the next number would be number 4. I follow the pipe all the way down, and there's number 4. That would be the inlet to the fan coil. And number 5 would be the outlet of the fan coil. Then I have a short piece of pipe from 5 to 6, and then the control valve, 6 to 7. Then from 7, I follow all the way along to point 8, and that's the inlet of the air and dirt separator. And then from point 8 to point 9 is the across the air and dirt separator. I could have put in a point here where the connection is for the expansion tank, but the pressure drop across an elbow, I'm sorry, across a T for an expansion tank is generally negligible, so I generally don't count that. And then, so the last point is all the way back to the boiler number 10. So now I want to set up a very simple spreadsheet. Hold on one second. I'm going to set up a very simple spreadsheet, and I'm going to account for all of these points. So with a little luck, my spreadsheet will work. I'll erase some of this stuff. And so I've set up a little spreadsheet, and if you'll notice, I've put the item number 1. So we're going to highlight this stuff here so you can see what's going on. So I've created a little spreadsheet. Actually, I created it on an Excel spreadsheet. I labeled it pipe and fittings. I invented this myself, so this is not something that you know, you can go out and buy somewhere. It's just a very simple spreadsheet. It's all manual. So for item number 1, point number 1 to point number 2. Now, if you'll recall from my diagram a moment ago, I said from point number 1 to point number 2 is from the discharge of the boiler to the suction side of the pump. And I'm just accounting for that piece of pipe. So my first process here is to document all the pipe. In this case, that piece of pipe is 2 feet long, 2 feet. So going back to my little table over here, I gotta erase that. So from point 1 to point 2, I have 2.5-inch scheduled 40 steel pipe, and the length of pipe is 2 feet. So I can highlight that just so you'll know what's going on. So I've labeled this point to point. Point 1 to point 2, under the description, I've told you what it is. It's 2.5-inch scheduled 40 steel pipe. And I have several headings: the equivalent, equipment pressure drop, the quantity, the equivalent length, and then the length. In this case, I just have a straight piece of pipe, so all I have is the length of pipe, and that's 2 feet. And if you notice, between points 3 and 4 is another section of pipe. In this case, that section is 20 feet. And from 5 to 6, that section of pipe is 2 feet. They're all the same size pipe. They're all 2.5-inch, but they're different lengths. And I'm just going to go back here for a moment, erase this. And I'm just going to go back so you won't lose track of what I'm doing. Again, from point 1 to point 2, that's a 2-foot piece of pipe. And from point 3 to point 4, that's a 20-foot piece of pipe. So from point 1 to point 2, that's a 2-foot piece of pipe. And from point 3 all the way down here to point 4, that's a 20-foot piece of pipe. All right. And all I did was make up this little chart and fill in all of that. For item number 6, it's no longer point to point anymore. I'm counting the number of elbows. So let's go back and count the number of elbows. So if I start at point 1, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 13 elbows. But if you'll notice on my chart, I put 20 elbows right here. And the reason I did that is because my diagram, my piping diagram is somewhat schematic. I don't know the actual number of elbows that are going to be required to install this system. So I've increased my quantity from 13 that I've shown in my diagram, and I decided to use a number slightly larger, 7 more than what I counted, so allowing for some flexibility. And again, the equivalent length of each one of those elbows is 6.5 feet. And if you remember, going back to our chart, let's see if we can do this. Going back to our chart, for a 2.5-inch pipe, a standard elbow has the equivalent length of 6.5 feet. So again, coming back to my table, I have 20 elbows at 6.5 feet. I simply multiply 6.5 by 20, and now I have the equivalent length of 130 feet. So above is the length of the actual sections of pipe, and now I have the equivalent length for the elbows. So if I just do my arithmetic out, there's 20 plus 20 is 40, 42, 44, 46, 46 and 130 is 176. That's the total length of pipe and equivalent length of fittings that's in my system. And the pressure drop in feet per 100 feet is 2.72. Again, going to my table for 2.5 inch, whoops, I'm sorry, I went the wrong way. Yes, here it is. For 2.5 inch pipe running at roughly 60 gallons per minute, it's 2.72. So that's how I came up with that pressure drop of 2.72 feet. So if I multiply 176, now remember, this is the pressure drop in feet per 100 feet. So I have 176 feet. If I divide that by 100, then I'd have 1.76 times 2.72, which is approximately equal to 5. Any questions about how I generated this pipe and fittings table and how I calculated the pressure drop based on the equivalent length?
No. Someone's mentioning control valve pressure drop. Did you? Is that included in there or
not yet?
Not?
This is just the pipe and the
Not yet.
fittings. We're
Okay.
going to touch
All right.
on
Thank
that
you.
next. Okay.
Yeah. Okay.
So there are the two tables we use. So now we're going to figure out what the pressure drop is for the equipment and the control valves. How's that for timing, Brett? So getting back, remember I said that I had the different points on my diagram. So I'm going to go back to my diagram. Let's go back to where I labeled them. So from the first one here, the very first piece of equipment would be the fan coil, and that's from 0.4 to 0.5 on my diagram. So from 0.4 to 0.5, there's my fan coil, and the equipment pressure drop, the only place you can get the pressure drop for this piece of equipment is from the equipment manufacturer. You cannot calculate that. You have to look it up. Whatever fan coil you chose for your system, you'd look at the manufacturer's data. And for that flow, in our case, it's a little over 60 gallons per minute. They publish the pressure drop, and in this case, it's 10 feet. The quantity in this case is 1. Equivalent length does not apply, and so the pressure drop is just 10 feet. Now, obviously, if I had in series, if I had 3 fan coils, then I'd simply change this quantity from 1 to 3, and my pressure drop would be 30 feet if it was 10 foot for each one. Now we have the control valve. In this case, my control valve is from 0.6 to 0.7. Let's go back to our diagram. There's 0.6 and there's 0.7, and between those 2 points is the control valve. So when I look at my little table here, I have my control valve has a CV equal to 50, but the flow is 61.5. So if you recall the equation I used before, I said I took the ratio of the flows, in this case 61.5 divided by 50, and that ratio comes out to 1.23, and I square that times the initial pressure drop of 1. My new pressure drop is 1.5 pounds per square inch. I have to multiply that by 2.31 to convert it from pounds per square inch to feet, which comes out to roughly 3.5 feet, and I rounded it off to 4 feet. Any questions about how I calculated the pressure drop for the control valve?
Nope. I think everybody sees that.
Okay, and again, highlighting the control valve, the manufacturer publishes the CV value for the control valve. In this case, the CV was 50, and that says that it has a 1 pound per square inch pressure drop at 50 gallons per minute, but our system is 61.5, so I have to adjust that for the actual flow across this control valve. The air separator was 0.8 to 0.9, and again, the only place I can get that pressure drop is from the manufacturer. In this case, it's 5 feet. And the boiler is 0.10 to 0.1, brings us right back to the beginning. And again, the only place I can get the pressure drop for that is from the boiler manufacturer. So there I have the values for all of the equipment and the control valve. And if I add that up, and let's say that's 10 and 11, that's 21, 25, 30, that's equal to 30 here, plus the 5, it actually was 4.7 in my spreadsheet, but I'll round it off. And that comes out to 34.7 or 35. So that is my calculated pressure drop for my simplified system. Okay. Any questions about how I manipulated, rather how I filled in these tables? I created the tables myself. I created a point-to-point diagram. I filled in the values. I either did the calculations or looked up the data, or a combination of the two. Any questions, Brett?
No, well, there's a couple I'm going to bring up, but I do want to make this comment. A person suggested that these are very, very, very nice charts and was wondering if you had a patent on them. It's in the works. Is that
It's
what
in
you're
the
going
works.
to say? So when you made the choice of pipe size, you used 8 feet per second. Was that a random number, or why'd you do that?
Well, again,
How'd you select that?
you know, most hydronic systems are designed for a range of velocities anywhere from 6 to 10 feet per second. And the most common value for hot water and chilled water heating and cooling systems is around 8 feet per second. So I decided, it's a bit subjective. I decided I wanted to have a velocity of less than 8 feet per second. And as I said a moment ago, you know, in this little simplified example, let's assume that it's a constant flow. It's not in reality, but let's assume it was. Then I would want to have a maximum velocity of 8 feet per second. If it was a variable flow system, I would probably design the piping system at a higher velocity allowance of maybe around 10 feet per second, knowing that the maximum flow in gallons per minute is probably only 1 or 2% of the time. And the majority of the time, the velocity is going to be less than 10 feet per second. And so I can conserve on pipe size when it comes to that approach. Okay.
There's a couple of comments about the boiler pressure drop.
Yep.
Did people say, why is the pressure drop on the boiler changed from 15 to 11? I don't know if you did change that or whatever. I don't know why people are saying that.
Oh, that's an
Anyways,
excellent,
I don't think
that's an excellent observation. That's a typo. I meant to put 11 over here. So there's something I have to fix in the future. That's a great catch.
Oh.
This value here was supposed to be 11. And so, no, I didn't, there wasn't anything special going on here. I just lost my head. I got so excited about the numbers. I put in the, I put in the wrong value when I typed it in. So that's a typo. So I'm going to put the big letters here, TYPO, TYPO. Thanks for catching that, because next time I do this presentation, I won't have to go through this silly explanation of why I typed in the wrong number. That was a great catch. You know how many times I looked at this, Brett, and never caught that before?
It's crazy how that happens.
I know it. It's cool though. Okay.
How does glycol affect these calcs, or does it?
Yes. So if you'll notice, let's go back here for a moment. Erase all that stuff. The table that I used for this pressure drop calculation is all based on water with a specific gravity of 1. So if you were doing pipe pressure drop calculations for, say, glycol, then all the values in the table would remain the same except for this value here. And this, in this case, it's 2.72 based on water with a specific gravity of 1. If it was glycol, you'd use a different pressure drop in feet per 100 feet. But other than that value, all the rest of the values remain the same. And if it was glycol, the equipment manufacturer would have a different value. So when you looked it up in his tables, his or her tables, and you looked onto fan coil, for example, this would be fan coil for water at a specific gravity of 1. But generally speaking, the manufacturers have correction tables, or they have different values for different fluids. So when I looked up the data for the fan coil, it was 10. That was based on water. If it was glycol, I'd have to look deeper into the manufacturer's published data and find out what the pressure drop they're publishing for different solutions of glycol. Hopefully that helps.
I'm sure it does.
Okay. So now we did the calculated pressure drop of approximately 34.7 feet. And then I have a second line here, which I call the total pressure drop. So the total pressure drop of the system is the calculated pressure drop. That's this value here. Let's kind of highlight this. That 34.7 feet times a safety factor. And in my case, I selected a safety factor, 15%. So with that in mind, that means that my total pressure drop in my system is 34.7 times 1.15, and I rounded it off to 40 feet. So if you do the actual arithmetic, I think it's 34.7 times 1.15, came out to like 39.9, and I rounded it off to 40 feet. So here's where it becomes a bit subjective. You can put in any reasonable safety factor that you want. The calculation is based on pure numbers. There is no fluff in the actual calculation, but this is when we go from a calculated value to the total pressure drop in the system. Some people might pick 10%, other people might pick 20 or 25%, and you can see it becomes somewhat subjective. So the total pressure drop was equal to 40 feet. And if you'll notice, the flow was always 61.5 gallons per minute. I tend to round things up. So when it came to the pump selection, I selected a pump at 65 gallons per minute at 40 feet. Ta-da! So that, in a nutshell, is how you do a manual calculation for pressure drop in a piping system. It doesn't matter, by the way, how complex the piping system is. The procedure that I've outlined here manually is exactly the same. Any questions?
Just one comment about the more complex one. You have to make sure, well, you should do them all, but you make sure you do the worst case, right? For sure.
That's correct. So when you're doing a manual calculation, you might have 4 different circuits or paths, in which case, if you're doing it manually, you'd have to do the pressure drop calculation for each path. And let's say we had 4 instead of 1, and then we'd pick the one with the worst case. So in our case, let's assume that this was the lowest value, 34.7. If I had 4 different circuits or paths that the pipe, and let's say they range from 34.7 to a maximum of 50, then I would use the 50 feet as the calculated pressure drop. So you can see it becomes very time consuming to do these calculations manually. But whatever procedure you use, and we'll talk about a different procedure in a second, they're all based on this science. Everything I've shown you is universally accepted. So the last slide, or the next to last slide, is that I actually did the same exact calculation using software, which is the HS2 software. If you notice, I have a little green thing because I didn't want to reveal it right here. There's that little green box right there. And with a little luck, I'm going to go to the next slide, remove that green, and you're going to see that it's 34.7. That's the same calculation that I did manually. So the software calculated the same pressure drop as I did manually. And that's because I used the same procedures in the software that I used for my manual calculation. The benefit of doing this using software is now the diagram becomes much more sophisticated, can have many, many more components. You can see I oversimplified this so that I could demonstrate how to do a manual calculation. But if I had 30 or 40 valves in it, or multiple pieces of equipment, or 10 or 15 different circuits, the calculation would be very complex. And the nice feature about using software is that it can keep track of all this stuff. But behind the scenes, The software is just doing the same exact thing that I did manually, only that it's doing it, it's automated. Okay, so with that, ta-da, get my handy dandy pen here. Any questions? I don't hear a rash of questions, Brett.
Oop, I had myself muted, so sorry about that. You covered most of them. In the software, someone's asking, how did you account for extra elbows? I'm sure you put a percentage in there.
Yeah, so
And,
when I did the software and I used the HS2 software, if you've ever gone through the software presentation that Brett does, he'll show you that you can either pick a factor for your fittings or you can put the fittings in one by one. I actually, because it was a simple example, I wanted to put the fittings in, so I chose 20 elbows by selecting the fitting option instead of the multiplying factor. I think the default for the software, Brett, for the multiplying factor is 1.5. Does that sound right to you?
yes, it is.
So because I wanted to show that you could do a manual calculation and a software calculation, come up with exactly the same values, I put the data in exactly the same way. Any other questions?
There is a question about how did you decide to choose a control valve with a CV of 50? Why not some other CV?
It was arbitrary, just to demonstrate that I wanted to pick a CV that was less than the flow in the system so I could show you how to make the correction. Typically, I would think that most control valves are probably in the range of, I'm guessing, they're probably a little bit lower than that. For this example, for 60 gallons per minute, they probably want a CV of about 40 because they'd want a pressure drop of somewhere around 5 to 6 pounds per square inch. It all depends on, your system characteristics, which I didn't get into a lot of detail here. So I picked 50 because I wanted to demonstrate how you make the correction from 50 up to 61.5.
And you did mention that for a plumbing system, these calcs were more based for an HVAC hydronic system.
That's correct.
For a plumbing system, the values are quite a bit lower, aren't they? Some of the, excuse me, I shouldn't say the values, but maybe some of the maximums that you might be looking for.
Yeah, typically in a plumbing system, you are using lower velocities. Plumbing systems, when it comes to HVAC, we're talking about closed systems with the exception of cooling tower, open cooling tower systems. But the majority of hydronic, hot water, chilled water for heating, ventilating and air conditioning type systems are heating and cooling. Those are closed systems. The water is treated. The chemicals reduce the amount of corrosion in the piping. In a domestic water plumbing system, you can't add chemicals to the water, so you're stuck with whatever the quality of the water is. The water can have air in it, it can have chemicals in it. And when I say chemicals, in this case, it could have minerals. And so you start putting domestic water through a piping system, it can corrode or erode is a better choice of word, erode the piping system quite rapidly unless you reduce the velocity.
Okay, excellent. I think we're at the end.
Okay, so I have just a few parting words. Let's see what we got here. Oh, we had a great look at this, Brett. We got how many do we have here? We have almost 500. Yep. Excellent.
It was
so,
over
before
500
I sign off, again, Rich Medairos from Taco Comfort Solutions, a Taco family company. We're very pleased to provide you with this Taco Tuesday training, and hopefully everyone got something out of it. Hopefully you did. And before I sign off, do we have any last minute questions? Anybody's dying to ask?
No, I think you covered most of them.
Okay.
We actually, well, no, go ahead. Say goodbye, and then I'll finish up.
So with that, I'm going to say thank you once more and stay safe out there and turn it back to Brett.
Excellent job, Rich. A lot of thank yous and good presentation comments from people. So thank you very much. Okay, a couple of answers to some questions. If the software that Rich showed in the presentation, or I shouldn't say showed, but he did have a picture of it for his diagram. You can download that HS2 software, HSS software from the TACO website. www.tacocomfortsolutions.com. Is that our website, Rich? I think I have it, right? I don't know. We've changed things so much.
Yeah, tacocomfort.com.
tacocomfort.com. And if you go to the apps page and software, you can download that software from it. And just to reiterate, you should receive an email tomorrow. If you don't, send in an email to where you registered, and Ken Watson will make sure you get the link. But we are taping this webinar, and you can watch it down the road. It'll be available 24 hours after this. So just keep that in mind. And in 2 weeks from now, the TACO Tuesday webinar that's more commercial focused will be on chiller plant design, how to lay out a chiller room. So that's kind of an exciting topic. So keep that in mind. So look for registration information there, or go to our website and you'll be able to register there. Other than that, I can't thank you guys enough. Thank you guys and gals, folks, enough for attending. And as Rich said, stay safe out there. And if we didn't answer your questions, we will down the road. So take care, everybody. Goodbye.